So yeah, we will be looking at how to improve the speed in your QML application. Well, more generically, we'll look at performance, which could mean a lot of things. So how long does it take for your application to start up? How smooth are the animations? How long does it take to react to user input? Well, shutdown, that's probably usually the one you're least interested in, but we will see there's even scenarios where you can create an application that takes a couple of minutes to shut down. That might not be desired either. And then there's also stuff that's not directly related to speed, but usually comes in as a side effect of poor performance as well. And that is high memory use and also high battery use or power use. The latter is obviously most interesting on battery-powered devices like phones. But even on laptops, that is still very interesting. We will be looking at 2 or 3 small QML examples that in the initial implementation perform quite poorly in some way or the other. Then we'll be seeing profiling tools to analyze that. We'll see how to interpret the results and how to eventually fix our application to be a lot faster. So the first thing we will be looking at is this little example. Let me switch to something where we can actually read the code. But before we look at the code, I just run QML Viewer with this application, which will take about 4 minutes to show up. So that gives us plenty of time to look at the code. Well, I assume you're all familiar with QML, at least with understanding the basics here, right? So we have our top-level rectangle, a few properties on it, small animation. And in there we have 2 nested repeaters, and that's actually the interesting bit. That's not updating here. OK. So there we go. 2 nesting repeaters. They create a number of more rectangles, assign some properties, and then have some magic JavaScript down there that calculates the color. Who of you has an idea what this will output? Well, we have to bridge 4 minutes until it's actually done. So yeah, there's one idea. A circle, yeah, that's going in the right direction. But you can't render a circle directly in QML, can you? So how will this show you a circle? So it will create lots of small rectangles in a grid. So we have 1 repeater for the lines and 1 repeater for each column. So we iterate over each cells in the grid and create rectangles for that. And we calculate the color based on the function down here. And it's still rendering. So if we look up here, how many rectangles are we actually generating here? Right, so 3,600 rectangles, that can't be that expensive, right? That's 3,500 rectangles. Well, QML should handle that. There's no reason why that would take 4 minutes. But we have made so many mistakes in that code, as we'll see once we start profiling that it's actually taking not only 4 minutes, but we will also see it takes more than 200 megabytes of memory to create this structure. And I mean, 3,500 rectangles and some JavaScript in there. that can't be that bad. Has anyone already an idea of what might be slow in here? So what will be the bottleneck? Any guesses? Yeah. So, right, the first thing that everyone thinks about is this fancy math and JavaScript in there, right? That has to be slow. Any other ideas? Yeah.
The two repeaters.
The two repeaters, okay. So we have two nested repeaters. That might have some side effects, indeed. Any other ideas?
Creating a rectangle in the very deepest repeater.
Why would that be expensive or more expensive than creating it outside?
Depends if you can create one modified instead of creating a new one at each direction.
Okay. Yeah, I think that's pretty much the order in which things came to mind. There's the output. So yeah, it creates 3,500 rectangles and calculates the color based on the fancy mask to render as a Pac-Man. So the initial idea when I was writing that was, well, with QML I can only do rectangles and images, so I want to do more complicated geometric forms like I can do in graphics view. So I just not use something like a pixel shader where I use JavaScript to calculate the color of each pixel. But that somehow didn't work out, and I had to reduce the pixel size a lot to actually get an output in a finite amount of time. So let's go back to the slides and see what we can do about this. Oh yeah, we didn't even see the animation here. So it takes 4 minutes to start up. It takes about 2 minutes to shut down. And if the animations are enabled, it's less than 5 frames per second. So for something as simple as 3,500 rectangles, this is way, way, way too slow. So let's see what we can find out about it. And of course, that means profiling. So let's see what kind of tools we have available to analyze the behavior of a QML application. The first one, or the easiest one to use, is an environment variable QML show frame rate. So if you set that to run and run any QML application, that could be QML Viewer, that could be your C++ application that embeds a QML or a declarative view inside, this will print some debugging output. Basically, for each frame, it will print you the time spent in painting itself, and it will print you the time spent between frames or between paint events. So that's at least something very, very easy to measure the animation speed. Well, that doesn't really help us here, right? Our problem is startup, so way earlier than that. But it's still useful once you start improving your application, especially regarding animation speed. This allows you to very easily check if you're actually getting faster or if you're getting slower without using all the more advanced profiling tools that are where you have to do much more work and wait much longer until you have easy results. So that's a very quick sanity check on your performance improvements. And then obviously there is the QML profiler in the newest Qt Creator. If we run that on our application, we'll get the output we have down here, which starts over here at the beginning of the application. And it shows it does some painting, and then there's 4 minutes of nothing, and then there's another paint event over here, and some tiny binding assignment. So this is not really helping either. It doesn't really show us anything during the startup. We'll see later on that this actually is very useful once profiling the animation speed or changes at runtime. But during startup, it's also yeah, not really helping here. So what else do we have? Quadrant. I mentioned that in my previous talk already. That's an instruction level profiler, unfortunately only available on Linux and Mac. So we are going way, way, way down the abstraction level, down to individual CPU instructions, counting how much is used in each line of code, and see what we find out that way. So yeah, this will give us number of CPU counts per line of code. That's way too detailed, way too low level. And it will give us number of method calls. That's still very low level, but it will at least show us some interesting behavior in the QML internals that might show us where we actually have the problem in our code. But yeah, in general, well, this doesn't only apply to QML, but to any kind of profiling. You need to make sure that you measure exactly the part you are interested in. So Quadrant has an extra command line tool, Quadrant Control, which allows you to enable measuring and disable measuring at certain points in time. It allows you to write out the current log to reset its internal counters and measure a different part again. So if you're only interested in startup, that's the part you want to measure. So you start profiling at the beginning. Once the application shows up, you stop immediately. You don't shut down the application, but you stop the profiling, and then you shut down the application. Because as I mentioned, our application also takes 2 minutes to shut down. So we don't want to confuse the shutdown speed with the startup speed. They might be somewhat related, but you want to isolate the areas you're looking at. Similarly, if you're measuring performance at runtime, animations, reaction times, you don't want to have all the startup part in there. You'll see things like parsing queue settings files for Qt plugins and stuff like this. So this is absolutely irrelevant for profiling runtime. So disable that, enable only for the part you're interested in. Makes it much easier to interpret the results. So that's what we are getting here. This is KCacheGrind, a very detailed visualization tool for Quadrant. You can also use the built-in visualization in Creator, but that's far less detailed, but might already give you a hint. So what we are seeing here is, it's hard to read. This method down here is QDeclarative regenerate. So it's somewhere deep in the internals of QML, completely unrelated to our code. But it tells us, just from reading the method name, that we are regenerating whatever is inside the repeater actually several hundred times. So whoever mentioned the nested repeaters, you, yeah, we have a problem there. What's even worse there, if you change the amount of pixels in this example, you will see that it doesn't scale linearly, but it's at least quadratic or even worse scaling. So if you double the amount of rectangles, it will actually slow down far worse than that. And that's actually triggered by the nested repeaters. So this at least points us that to the repeaters as a cause for the problem. We'll still have to see why this is actually slow, but at least it gives us some hints in where we have to look at. So, and then we have the profile of shutdown. And there we see like nearly 100% of the time is spent in QObject disconnect. So the 2 minutes at shutdown, we actually spent disconnecting signal slot connections. So that also gives us somewhat a hint that we probably have way too many signal slot connections, which also could explain why the startup takes so long and why we need so much memory. And that we probably also have way too many QObjects. So only looking at the effects, we can draw some conclusions on where we have to look for optimizing this. So what else do we have? Right, I mentioned this also uses a huge amount of memory. So another tool I also mentioned in the previous talk, sorry for the duplication. Massive, also based on the Vagrant suite, so also only available on Linux and Mac, unfortunately. That is a heap profiler, so it will show you where your memory use comes from. So where the memory was allocated that we are using it at one time. And yeah, even if memory is not your primary concern, but well, if you use 200 megabytes for just a Pac-Man, it's probably your concern as well. It gives you some helpful information on where your performance problem actually is. So let's look at the result. That's a tool called Massive Visualizer that can nicely print out the visualize the logs you get from Massive, which is unreadable text files. And if we look at that, we use slightly more than 200 megabytes of heap space. And we can look at where this is actually coming from. And that's stuff like the Q vector that holds the connection list for Q objects. So another hint that we have way too many signal slot connections. And I think it's on the next. No. Right, we see that the connection list is in there quite a lot. We see 50 megabytes for declarative binding objects. So there's likely something wrong with how many signal slot collections or bindings we are creating. So yeah, now that we have gathered some data, done some profiling, we need to interpret that. And yeah, especially if you're targeting embedded hardware or mobile devices, many of those tools might not be available on your target system, or the target system might be way too slow to actually run something like Vagrant on it. So for some of the problems, you can actually run the same measurement on your desktop system, big, powerful workstation, and you will get the same results. However, some of the other performance-related issues are highly platform-dependent. Let me get some examples. Anything related to JavaScript execution, QML parsing, Q-object communication, that's all the same everywhere. So if you measure that on your desktop workstation, the result is very likely also applicable in exactly the same way to an embedded device. It's running a lot slower there. But anything related to painting, the windowing system, floating point operation on a CPU level, that is highly dependent on which platform you're running on, right? On an embedded system, you might have QWS. On your workstation, you might have X11 or Windows. So if you have any painting-related issues, that might behave completely different. Same for floating point operation. Another common thing, especially with embedded, is very different queued compiler flags. Especially for ARM and also type of floating point operations, there can be a huge difference how you compile queued for your target system. So if you don't profile on the target system directly, anything related to that might be completely different and might not confirm what you're seeing on the target system. So you always need to ask yourself that when interpreting the results you measured, is this actually what I'm seeing on my target system, or is that something that might be completely different, or am I looking at universal things that apply in the same way everywhere? And the things we looked at, we will see are universal. So let's get back to this code and see what we saw there. We noticed the repeater is regenerated several hundred times, so that's much more than we would expect. we saw an enormous amount of resources used for property bindings. So we have 50 megabytes of heap. That's 1/4 of our total heap usage for Q declarative binding objects. We'll see details on how binding works in a second, but just so much. They heavily rely on signal slots. So that kind of explains why we have these enormous memory structures for signal slots. And yeah, looking at the output there, we see that we have about 120,000 signal slot connections. So for 3,500 rectangles, something is clearly wrong there. And yeah, it points to bindings. So we'll have to look at that in a bit more detail. Yeah, I guess most of you are familiar with property bindings from QML, right? Anyone never heard about property bindings? OK. Yeah, as you know, that's the cornerstone of the QML language. It's like what signal slot connections are for Qt in the C++ world. It's the standard way to communicate between elements in QML. So you just write something like with colon half of parent width, and whenever the property on the right-hand side updates, my left-hand side will update automatically as well. And of course, the way these updates work is with signal slots. So if you ever implemented properties on the C++ side, you know that's the QProperty macro. You have to add to your QObject. But if you want the QML property bindings to work, you also have to add a notify argument to the QProperty macro. And there you have to specify a signal that informs you about the change in that property. So that's why we are getting so many signal slot connections here. But yeah, QML is declarative. So we just say what we mean. We don't say how it should be executed or in which order it should be executed. And that is, especially if you're coming from the C++ world, that's not something you're used to. You're used to stuff being executed in the way you write it down. And that's what you have in mind while you're writing QML code. But we'll see that, well, Murphy's law, so the order will be the worst possible combination in practice, the one you never had in mind, the one is least efficient. And you have no control over that because it's declarative. And yeah, so let's see what actually happens in code there. Let me switch back to the full code view. Let's see what could trigger a reevaluation of the repeater. Scroll that up a bit. So we see the inner repeater has a property binding on model, which decides how many rectangles it will generate, right? On root.width and root pixel size. So now if you look up there, those are basically constants, right? So why would that ever be triggered again? Now that's because we are assuming this is the order in which it's written. So the stuff above there will be set, and then the stuff in there will be evaluated. However, that's not necessarily how it happens. It might be that the property binding down here is set up first, and then the width is set, and then the pixel width, pixel size property is set, which would trigger 3 reevaluations of that repeater already, right? So the initial one with both depending properties not set, and then once the first one is set, it will update this. because you get a change signal as soon as you set the width, and that will update all existing bindings. And then it will set the second property up there, and that will trigger another change signal. And you will, again, reevaluate all the bindings. Now, if you go a few lines up, the auto repeater has basically the same problem, but it has the additional effect that whenever you change model, it will regenerate whatever is inside of it. So every reevaluation of that binding will trigger a complete recreation of the repeater inside, and might therefore cause like cascades in property changes. So a tiny change in one of the properties up there will trickle down through all the dependencies and several times regenerate the repeaters. And yeah, the thing we usually miss is that this is not a constant that is there from the beginning, but it's set once and then will update all existing bindings. So that kind of explains why we have so many repeater regenerations. Now, how can we fix that? Okay, here we have the slightly improved version. First thing we do is we get rid of the nested repeaters. So we eliminate these very, very expensive cascades of property updates. So we limit the depth of the update as far as possible. And just by slightly changing the math and having basically look at it like for loops. So instead of having two nested for loops, you can just have one, and you do some clever math on the index, and you can calculate which position you are in the grid. And that will already help a lot in terms of propagation of property changes. And yeah, well, this Pac-Man thing obviously is a very artificial example. But these kinds of property binding cascades actually happen in real code. So that's something to keep an eye on, that you don't have this, especially this exponential growth in updates. If you're having C++ properties, a common mistake you can make there is share update signals. It's like, why do I need to create a signal for each property I add? Kind of just have a general change signal and then just emit that. That will just amplify those problems, because everything that's bound to any of your properties then will also update, and anything depending on that will update. So isolate the change notifications, make them as small as possible, and limit the scope of the propagation wherever possible. So but this doesn't really give us much yet. That solves the problem with the nonlinear scaling, but it's still way too slow. So because we still have at least 3 regenerations of the repeater. And the repeater is 3,500 rectangles, so that's still very expensive. Let's see if we can reduce that further. Even up to 4 times, OK. Obviously, we only wanted evaluated once, right? Because the operation is so expensive. Anything that would trigger it more than once is not acceptable. So now the easiest way out is to not use a property binding. In this case, it's basically constant, so I can just put in the number there. And we won't have a single regeneration of the repeater code. So that already, compared to the binding solution, speeds up things by a factor of 4, because we only have 1 regeneration of the repeater. However, well, that's not what you want to use in clean software design, right? Just randomly adding constants somewhere, inlining whatever you had above there. Or in real-world code, you might actually have stuff that depends on something else that is not actually a constant. Still, we have one trick around that. This is well, if you work with bindings, you know that if you ever accidentally assign to a property that has a property binding, you will break that binding. So if you have an event handler in a mouse area, and yeah, as a result of that, want to update a property, you can just write property equals new value. And if there was a property binding set on that property previously, it will be gone now, and it will be now set to this specific constant value. Usually that's an effect you want to avoid, because you carefully set up your property binding. You don't want to break it by a simple assignment. However, assignments are not really declarative. They happen in JavaScript code, which is imperative, which is something where we have control over the order and over the timing. So even if it's not really clean in the QML way, we can actually use that to fix our problem. There's a signal handler called onCompleted. That's belongs to the attached object component that you have on every QML item. And that's called whenever the entire thing is completely set up as far as QML is concerned. So all the properties we might want to refer to exist at this point and are initialized correctly. So if we use that instead of our property binding on model, we bypass all the declarative stuff and use one imperative assignment where we have full control over the timing and the number of executions. So from the pure QML point of view, this is still very dirty, but it fixes our problems. It allows us to have, to depend on other properties, on external input, and it allows us to avoid the multiple evaluation of or regeneration of the repeater. Of course, this will not update model whenever any of the other properties changes, which is exactly what we are trying to avoid here. So less dirty than a constant, still quite dirty, but helps us with the problem. Unfortunately, there is no real nice solution to this problem. Since you have no control over the declarative language, there's nothing you can do about it. So you can work around with ugly hacks, but there is no really nice way to solve this. So this fixes our repeater problem, but that's only part of it. This, for example, doesn't explain the huge amount of declarative binding objects and the huge amount of memory we use for signal slot connection. That's actually caused by the huge amount of convenience properties and helper properties we defined in there, especially the ones we defined in the rectangles, because we create 3,500 of those. Each of them had, I think, 4 properties, so that's 10,000 or 12,000 extra declarative binding objects. Each of them consists of at least one Q object and has signal slot connections to the depending bindings. So that's where all this memory use comes from, and also the long, or part of the long startup time. And yeah, there is also no really nice way to optimize that. The only solution is to use less properties, especially in hotspots. So if you create hundreds and hundreds of items of a specific type, try to reduce the amount of properties in there. What we'll be doing here in the example is kind of inlining the convenience properties. So the calculation we did there once just to make the code cleaner and to, well, maybe optimize it as you would do in C++ code. That's actually hurting here. So we inline whatever we can, and we move stuff into JavaScript. Because it turns out that executing JavaScript is actually a lot cheaper than all the property stuff we did in QML. If you create helper variables in your JavaScript code, you barely notice that in the output. Which is, if you think about it, hardly surprising, because the JavaScript engine behind that, JavaScript core used in WebKit, and V8 in the QML2, that's highly optimized stuff with just-in-time compilers and all kinds of optimizations used in modern web browsers. And this stuff is supposed to deal with megabytes of JavaScript frameworks you find in modern web applications. So the 2 extra lines we might add there, this doesn't matter at all. So it's a lot cheaper to have stuff in JavaScript than having QML properties defining the same convenience variable for you. Of course, that only works if you only really need that in this JavaScript and not really need the property semantics. So this is our version that inlines all the helper properties we had in Rectangle. So in the earlier version, we had 4 properties there, calculating the indexes in the grid and the position. That's now inlined. The constants are inlined where possible to reduce the number of bindings to top-level properties. And you see we moved a lot of more stuff into the JavaScript for the color. This is, of course, not the nicest way to write code, but that's something you would only do in real hotspots in your application. And the effects of that are quite dramatic. So we have overall a speed up of a factor of 250. So from 4 minutes, it goes to basically instant. We only have 1/10 of the heap usage, so about 20 megabytes. And we actually doubled the speed of the animation. So let me show that. So nothing near the 4-minute startup and huge resource use we had before, and even somewhat decent animation. Of course, now the code is very ugly, but yeah, in reality, you would find some kind of trade-off between clean code and fast application. So concentrate that on the real hotspots. In our case, that's the 3,500 rectangles and the nested repeaters. And of course, afterwards, it's a good idea to verify that you actually improved things. In our case, it was so obvious that we don't really need to look at the timing anymore. But if you look at the memory profile, it now peaks at about 20 megabytes. And you also see that the time distribution is totally different. So shutdown is nearly instant now because we got rid of all the expensive, or most of the expensive signal slot connections. Yep. So is this actually a relevant example in practice? You wouldn't really write a pixel shader like that in QML. But yeah, there's actually a lot of relevant stuff in there. If you have real-world application, they easily can have hundreds of property bindings. And all the measurements we did here is my powerful workstation laptop thing. So that's quad-core, lots of memory. if you run the same application on an embedded hardware, like 300 megahertz ARM, this, of course, will be amplified by a factor of 10 or so. So if I had a problem with 3,500 rectangles and 4 properties in each of them, if you run that on a much smaller hardware, you already run in problems with like 300 items and a lot of properties. So this is actually relevant, especially if you're targeting low-end hardware. And yeah, bindings, this is the cornerstone of QML. So you will use that no matter what. So it's really important to keep in mind what the side effects are and how, if you can avoid like only convenience properties that you don't really need, or move them to an higher scope where you only have less instances of the same object, then that can help optimize your system. Yeah, of course, then the next question is, should I use this binding stuff at all if it's so expensive? Yeah, and of course you should, because that's how QML works. If you don't use bindings anymore, then yeah, what's the point of QML? That's the key aspect of it. And it's really only a problem if you have large quantities of that and yeah, put them in single hotspots. As we saw, if you have the option to avoid them, like moving more code into JavaScript, that actually gives you a considerable speed up. And yeah, we noticed that bindings cause us problems at startup. So the creation and setup time is quite expensive. You create a couple of Q objects, you set up all the signal slot connections. And we also saw destruction is quite expensive. Updates, of course, whenever anything changes, it propagates. So make sure you keep the change notifications as small as possible to avoid these cascades. Now we have focused a lot on startup time. So maybe that's not even relevant if you're writing like a control panel for an appliance that is running all the time. So you don't care about startup, right? It's only about runtime speed. However, what we looked at, startup time is actually occurring at runtime as well in a number of places. Basically, whenever you dynamically create QML objects at runtime, and that could happen in a QML loader, so if you're loading dynamic parts of your application at runtime, or most importantly in the list view and path view classes. There you have delegates for each visible item in the model, which is basically a QML tree with whatever you put in there. It could be arbitrarily complex. And those are created at runtime whenever you scroll through the list. And of course, the same costs that we saw at runtime occur whenever you do the dynamic loading at the startup cost we saw also occur at runtime here. And yeah, in some very extreme cases, we had that recently in a project with, I think, a 300 megahertz ARM system, no hardware acceleration whatsoever, limited memory. And it was supposed to show a fast scrolling list view with 10,000s of entries. We didn't really manage to get that fast enough with QML because the item construction and destruction for the individual delegates was too expensive and slowing down the scrolling speed on such a low-end hardware. So what we ended up doing is we put a normal list view from the widget world on top of it using a graphics proxy widget. That's, of course, also a very, very ugly hack. And usually, it's recommended to not use graphics proxy widget. But widgets still have one advantage. They don't create new objects for every element that's shown in a list. They just have an existing delegate object which paints every item in there. So scrolling is just limited by painting, not by object creation and destruction. But yeah, this is kind of the extreme low end combined with extreme requirements on large lists. there you are clearly hitting the limits of what you can do with the design we have in QML. But then you still have the option to fall back to other methods to show the same content, for example, using the widget stuff. OK, so far we focused on bindings, so we get to that in a second. Bindings being one of the core elements of QML. So I think that's probably the most important and widespread thing to look at when profiling QML applications. In the remaining time, which is unfortunately not that much, we'll look at a number of other areas that are also often involved in performance problems. But this is the most common one, and the one you will probably find in all QML applications. OK, so the next one involves solving differential equations. So again, I did something with QML where it was actually not really designed for. And it exposed another interesting issue. So let me get rid of this guy. And yeah, this goes back to one of my coworkers coming up with some math puzzle he wanted to solve. You have 3 dogs positioned in a triangle, and the one in the left upper corner starts running towards the one next to him. This one starts running towards the guy at the bottom, and this one follows the one at the top as soon as we release them. And you want to figure out where do they meet and when do they meet. So you can do that with complex differential equations, or you can do that with a few lines of QML. And if I release them, you'll actually see the result and see them where they meet and when they will meet. You can even configure mass and acceleration and all of that in QML. But what's the problem with that? See, the startup time is perfectly fine. Execution is smooth animations. It reacts immediately. Well, it looks like there's no problem, right? So if I keep that running accidentally on my laptop, we will notice shortly afterwards that my battery is dead. So something in that application drains my battery. And yeah, how do we figure out what's causing this? So again, we need to have a look at the various profiling tools and see what we can collect there. The first one we'll be looking at is PowerTop. That's a tool, unfortunately, only available on Linux. And that shows you by process how much wake-ups are triggered on the CPU there, and it shows you the power-saving states on the CPU. So especially if you have to conserve power because you're running on a battery device, this is a tool you always want to use. And it will give us this output showing QML Viewer at the number 1, causing 60 wake-ups per second, and not really allowing my CPU to go into the energy-saving sleep state. OK, that doesn't really tell us anything new because we kind of expected that QML was causing this. But it helps you to actually verify that it's really your application that is causing the problem, or the other way around, tell your boss that you are not causing the power drain. It's some of the other stuff on the system. So that's the first indication that you actually have a problem there. So our second try was the QML profiler in Qt Creator. So down here we have the profile over time. Up here, that's the painting, and up here is the binding. Down here is the binding update. And that's the entire time span we run the application. So initially, we see there's nothing, right? All right. And then I click on the button to start the simulation. And then we see some binding update and some repaints, like the animation going on. So that's expected. But somewhere around here, it actually stops. So the dogs have met in the middle. We have calculated where they will meet and when. So, but yeah, it seems to go on. So there's binding updates all the way down. There's repaints all the way down. So something is happening there. Also, we are not seeing it on the screen. So let's see what that is. And our tool of choice for that is the QML debugger in the latest Qt Creator versions. Or any other object introspection tool would work as well. But what Creator shows us here, if we select one of the doc elements, we have X and Y here that they're marked red, so the properties are currently changing. And we'll see that they are changing in, well, in very, very small quantities. So we have position changes that are so small that they're way below 1 pixel. So we are not seeing it, but the animation is still going. And it's still iterating in the animation. And it's never going to stop. And QML obviously doesn't recognize that and keeps repainting with 60 frames per second. And that will drain our battery. Yeah, that's what we just discussed. Yeah, how do we fix that? The obvious approach is to disable animations you don't need anymore. Sounds too obvious maybe, but this is actually, even if the example is quite artificial, this is something that will happen in reality at least once new application. You will forget one of the animations running in the background. You don't see them on the screen, so it looks all fine. But it's still running, it's still updating properties, and every, well, this, 60 changes per second, you get, in the best case, you only get property change notifications, but we saw earlier that that could already have quite some impact. And in worst case, if you are triggering a repaint and draining even more power without actually seeing anything. So the animations in QML have an enable property, which you can use to disable them if whatever you are animating is not visible, or if the changes are actually getting too small. And what we are using in the example here were spring animations, and 3 of them combined together. And spring animations have an additional property called epsilon, where you define the smallest amount of movement that needs to be there to still keep going. And if it goes below that, it will stop. That usually works fine if you have only one spring animation. If you combine 3 of them, they will just keep going, so you need to explicitly disable them. But the more common case is that you have something like a loading, some spinner animation that you show while you're loading some data. Usually that's an individual page you put into the foreground while your model is populating or something like that. And once that is done, you hide it. But you keep the animation running because it's just like one busy page item. You didn't even look at the implementation. So it's not visible anymore, but the animation is still running in the background. And that's actually a very common mistake. So when you implement something like that, always make sure you disable the animation when it's not visible. Easiest way is just to bind to the visible property of whatever you are animating to solve this. Yeah, we didn't really look at the code due to lack of time. So let's skip that. OK, we only have like 3 minutes left. The 2 things that are, well, I think we have seen the 2 most common performance problems in QML, at least in our experience. What we will be seeing now are the two most common things that are blamed for bad performance in QML applications, but that are usually dwarfed by the other two. The first one is painting. Right, that's lots of updates on the screen. That has to be expensive. But usually it isn't. Unlike the two we saw before, this is one that highly depends on the platform you're running on. And especially with QWS or any embedded system, you can have interesting effects if the hardware has a different native image format than what you're using. And that can easily cause a slowdown by a factor of 2. So look at the no system background and opaque paint event attributes. If you set them in the wrong combination for your specific system, that might force an extra image conversion internally while rendering, which usually gives you a factor of 2. So that's something to look at, especially for QWS. On very slow systems, you might actually run into performance problems with rendering text. But again, we only saw that on a 300 megahertz ARM after optimizing all the other stuff away. And then you can do some caching in pix maps, like you would do it in a widget world as well. But if you ever get there, then you have probably fixed 90% of the other performance problems already. This stuff is very often blamed to be the performance problem. But it really isn't the problem. The other one that is very often blamed for the performance, and we actually had that in the beginning, right? JavaScript. We are used to C++, so JavaScript has to be a lot slower than what we are doing in C++. But as I already mentioned, usually that's really the fastest bit of the entire QML system. So the more you move in there out of the QML, the better, actually. OK, now I'm really running out of time, I think. Yeah, do we have any questions?
How much of these things will also apply to the QML2 in Qt5?
Honestly, I have no idea. The internals of QML2 are still changing as far as I know. I haven't really looked into it yet. Especially the stuff we saw with property bindings, especially the cost of them, is very dependent on the implementation detail of that. From what I know, most of the work in QML2 actually went towards the scene graph. So that's kind of unrelated to property bindings. I'm not sure what they did there. They changed the JavaScript part, which also plays into the bindings a bit because the expressions are actually passed as JavaScript. But I'm not sure if they changed the fundamentals of the binding system. So that would need to be tested. OK?
OK, thank you for the talk. Two common but quick questions. What about the anchor binding? Is it cheaper than assigning the width to the parent.width?
You're thinking about rather using manual layouting and setting size and positions directly compared to the anchor layout. I've seen several advices to do that instead of anchoring, but I don't think we have seen actual improvements when trying that. We played with various combinations while doing the list view I mentioned on the low-end hardware. The thing that obviously speeds it up if you assign constants to position and size, but that doesn't give you any layouting anymore. I can't really answer that from the top of my head, but I don't think there's a big difference between anchoring and manual layouting.
Okay.
Because it's both property bindings.
Thank you. Another point is if the property binding is so expensive, why not just use a JavaScript function call? I mean, this should be very cheap. So I mean, you could even inline the JavaScript function call. So you just do brackets, then calculate and return.
Yeah,
it.
but
so.
We saw that in the color function, right? That is JavaScript code instead of, well, it's not really instead of a property binding. This actually is also a property binding because we use properties in there from the outside. And it will also update or reevaluate the JavaScript whenever you change those. So there's really no difference between having JavaScript code there and like a normal binding. It's all passed as JavaScript, and there's one optimization in there. If you assign a property without any changes, or I think they also support just addition and subtraction. But as soon as you do anything more complicated, it is actually the same as the inline JavaScript function. So the execution of the code in there is fast, but the updates and the setup you need to actually make that property binding, that's the expensive part.
Thank you.
OK. And Thorsten?
For your list problem you had there, wouldn't it be possible to reuse some items so you don't need to have 10,000 but only 10 which are visible?
Oh, you mean reuse the existing instances of the delegates? There's actually a cache option in QML list view so that you don't immediately destroy items that are no longer visible and recreate them. But it does actually not work the way you described it, by just keeping them around and updating them when they come in again from the top. But it's just keeping around basically the sliding window about where you are. So as long as you move around there, it reuses existing ones, but it just creates a lot of them. It does not move them from the bottom to the top while you're scrolling. That might be an interesting optimization, but that's not how it's currently implemented. OK. Any other questions? No? OK, thank you.